Where is everybody?
Oh. Everybody's at the department meeting.
As you said, yep. But it's, I mean, it's okay, if there is another slot available, we go over the talk again, because it's very broad topic, and I learn also a lot while presenting and
Yeah,
preparing it, so.
like, I think in a way it might work better. So another alternative is you just record the talk and send the Zoom link to me.
Yeah.
I will send it to the department. And then everybody can watch the talk in the comfort of their home,
That's, okay, so,
What do you want to do?
yeah, let's go over the talk. Hello, everybody. I know there's a conflict, a departmental meeting. Sunil is here, so we'll have this talk on with small audience, and I hope it is recorded well enough for you to watch later in case you're interested. I need to mirror because it's. Oh, I see. And the main goal is to try to compare different viewpoint or angle to see mathematics that can be learned through the history of mathematics, the way it developed, and then also to get some bigger pictures instead of the usual detail-oriented definition, theorem, property details as most of us are used in content courses, articles and all that. So that's one thing. And the other one is to look at some breakthrough moments in the development of mathematics, which marked the development not just in mathematics, but also physics, sciences. And one such moment we all know, it's Galois' breakthrough solution to a very important problem, which polynomial equations are solvable by radicals. And also the slides, which are available from my webpage at ISU. These slides will have some color codes. Red, I suggest some students might be interested in going to see the details. Usually I use Wikipedia for those details. Again, Wikipedia doesn't go to a technical level, but from the first paragraph, introduction, you get a general idea about what is that concept. And then, of course, when you have time to take an abstract algebra course or analysis course, then you learn in depth, but usually you don't have so much time, so many courses. Okay, so from the beginning, try to have this analogy that when you look at some reality, say Rocky Mountains and so on, from the distance, you still enjoy the landscape. You don't see the details, and then you could try to go over there and climb a little bit, but then some parts of mathematics are really not so accessible for everybody, so you just learn what you can, in some sense, from the distance. I'll skip more such advice. So regarding programs in mathematics, this refers to breakthrough new ideas. Let's call them programs, and they are associated with top mathematicians, which we should learn a little bit about in time, of course. So I'll focus on Galois, Klein, Lee, Noether. I wrote Hilbert here, but I didn't have time to go over that in the slides. Lagrange and much more, but Lagrange and beyond his far-reaching program will be addressed in a second part of this talk in the current Applied Mathematical Seminar, October 24th. These programs and presentations became like principles that changed the landscape of mathematics and led to advancements in many other areas, sciences. For example, the role of symmetries and groups of transformations is crucial, for instance, in physics, to classify elementary particles, in chemistry, to understand molecules, and biology, and so on. So this part one will briefly go over Galois, Klein, Lee, and Noether. And without too much history, but I provided a link, and in 1 hour, of course, I cannot do justice to all these great mathematicians and the ideas introduced. So feel free to go to Wikipedia and read a little bit about them. Starting with Évariste Galois, this is a good example of what a bright young man can do without too much formal education, but passionate about mathematics and achieving some remarkable steps and introduce new ideas in mathematics that marked the whole development later on. The problem he was working on is what polynomial equations have algebraic formulas for their roots in terms of coefficients. The term is solvable by radicals, and there is a precise definition for that. Again, I won't give the details at this point. Just an example, quadratic equations have the so-called quadratic formula, and you all know it. It gives the roots of the equation in terms of the coefficients of the equation, in terms of arithmetic operations and square roots. Now, this turned out to be a difficult problem, not knowing exactly how to approach it. So his brilliant idea was what I will call Galois principle. And I'll generalize it a little bit, make it more or less technical. To study a mathematical object or problem, look at its group of symmetries, associate a group of symmetries, and then study that group. Retain this briefly, going from the object to its group of symmetries. Any comments, Sunil? If you have an idea or like a comment, then it will be more interactive.
No, I think that's actually a very important problem in the. But the thing, the comment I want to make is that when Galois developed the Galois theory, it not only solved this problem, but it also provided solution to several other problems of antiquity. including the doubling of the cube or trisecting the angle problem. The ancient Greeks were fascinated with this problem. Can you trisect an angle using straight edge and compass? And that remained as an unsolved problem for almost 2 millennia until Galois came up with the solution. Galois theory provided a solution.
Thank you for this. I didn't know about this side of his work. I only was aware of Gauss's work in this direction, and then his breakthrough, say, result when he was 17, that only those certain regular polygons can be constructed with ruler and compass, and that's again another beautiful part of abstract algebra, algebraic number theory that meets geometry. So so that's I guess much more to be said about Galois. But thank you, Sunil, again. And let's retain regarding this, I'll point out this say important problem, because later on I will speak about Lie and the corresponding problem for differential equations. So pay attention to this, and then let's try to connect with the more difficult case of differential equations, and when is a differential equation solvable, but not by radicals. So there you need integration. So by integrals in a certain sense. And then while preparing this talk and learning about these two separate areas, I started to realize how much similarity is there between the two, and that's always a good feeling. So I want to share it with you also. So differential equations, which will have associated the so-called differential Galois group. And again, here we talk about solvable by radicals. And here solvable by integrals. And I'll disclose a little bit the similarity. We all know that when the modern approach is to look at field extensions or joining symbols, like for example, Q of I as an extension to solve polynomial equations like this. Turns out that there is a similar theory where you join formal solutions and I'll say more about this later on. It's part of the so-called Picard-Bessieux theory. So the upshot of this is that later, when you study, for instance, differential equations, knowing about Galois theory and the approach gives you some feedback in a more difficult area. Feedbacks are always useful. So let's retain again this idea to an object which we want to study, associate a group of symmetries, then study that. So we need to learn more abstract algebra. Since time is of essence, I'm not sure if I will go completely through all these slides. But at this point, I want to emphasize our journey through mathematical education and point out some levels as if we are taking steps or maybe moving from one floor to the next. We first learned about numbers, then functions, operators, but then it's good to learn that we can group these objects by categories. And we don't need to know the technical term of what a category is, but use the intuition behind the English term. We group these objects by categories, which we can call mathematical structures. And then we look at our objects of our study, like groups, rings, fields, and so on, or topological spaces, or compare with one another, which are the so-called morphisms in the language of category theory. And then there are standard constructions between categories. So you take an object of one type, for example, a group, and then you construct the group ring, and we don't need to know exactly what the group ring is right now, which is an object of a different category. And this standard construction is a functor. And since we talked about group rings, of course, there is the other way around. So Neil studies what group of units are there of rings. So going from rings to groups. And then these are two standard constructions which are very much related to one another. And we call it a pair of adjunct functors, similar in some sense to how linear operators have an adjoint. And then the next level will be that of natural transformations connecting such functors. But by now, obviously, we are at level 7 or floor 7, 8, beyond the usual abstract algebra. But it doesn't mean that we shouldn't learn the basics of category theory, at least informally. Anyway, and that's one other point I want to emphasize in this talk. To learn a little bit informally, the same way we're learning a natural language, get used to the terms and then leaving the details and the thorough training for courses dedicated to that area. And maybe, so I would say, add big words like salt from first grade. There's some stretch here. I know not everybody likes these kind of statements. But for example, using the term category, which in English has a clear meaning and somehow suggest what we're trying to do with mathematical structures. So use those terms and then groups of transformations. And then students won't be shocked, or they will be prepared to learn more about these keywords. So now let's start with, actually continue with Felix Klein and abstract geometry. Felix Klein, one of the great mathematicians at the end of the 19th century, unified geometries which started to proliferate. So from Euclidean geometry, then we had non-Euclidean, Boyai, Lobachevsky, and so on. Then we had projective geometries and affine geometries. And at this stage, we don't need to know exactly what characterizes each of these geometries. But there was a clear need for a unifying view regarding what a geometry is. And then he defined abstract geometries, said briefly. An abstract geometry is a group acting on a set that makes that set a space in the sense of geometry, meaning that in that space you know what transformations are allowed and which ones are not allowed. But in an abstract way through a group of transformations, without defining some other concepts like angles or distance, which are the usual ways to talk about geometries. And with this, I'll include a remark regarding generalization that here the group acts on a set. It's kind of a minimal setup. Set category of sets, it's without further structure. But then notice that vector spaces are really what? Abelian groups. So you have vectors you can add, and then on top of that you have multiplication by scalars. So that's the action of a field on an abelian group. So what I'm saying is that this idea of group acting on a set can be then pushed further with more structure and start to look at group representations which are linear, or groups acting on a vector space, and much more, adding more structure. Structure which is really very important, but is missing from abstract algebra.
So a quick question.
Sure.
So around the same time, Poincaré had a different approach to geometry, right?
Poincaré, yes. So I taught history of mathematics and I learned so much about mathematics. So I encourage everybody to take a shot at that. What I remember Poincaré for is more for the introduction of topology, analysis, situs. So, but he also had contributions to geometry, to non-Euclidean geometry, had the models for hyperbolic geometry. But otherwise, I'm not sure if he tried to unify geometries in some sense.
And actually, I know that these two were rivals. Klein and Poincaré, they didn't get
Really?
along. Yeah, they were a bit of fight between the two.
Oh.
So Poincaré was not a fan of this program of Klein.
Klein, oh.
Yeah, and anyway, so that's another story.
Well, it's another story, but it's very interesting, and later I will share with you that I was looking for partnerships in such developments, and for example, Felix Klein was a friend of Sophus Lee. So Felix Klein started this research and development to unify geometries inspired by Galois. But then Sophus Lee wanted to do something similar, but with differential equations. And obviously, being friends and talking all the time, they benefited from one another. I think they also disagreed on that also. So this shows that we should learn not only about mathematicians in isolation, but also have these kind of short stories and understand how they influenced each other. They were friends, talking to one another. Are we talking to one another here enough? Maybe not, of course. Anyway, so Sunil shared this story that they were, Klein and Poincaré were really rivals in some sense. And indeed, that's the other side of the story. For example, Newton and Leibniz, they were disagreeing on how calculus to develop and so on. But you learn from these stories. Anyway, so coming back to Klein, abstract geometries, so a group acting on a set or vector space. So this shows how important representations, group representations are. It's And then this term of action, which usually think of that as a binary map, if you want. A category theory point of view would recommend to look at it as a morphism. So from G into, and if it's a group, automorphisms of the set in the category of sets. Then retain the term action as an intuitive term, but rephrase it, think of it as defining a morphism from one object to say the symmetries of another object. But this other object is in a different category. This is more abstract. But for example, in our case, sets are more concrete. So, and this shows that representations of an object, of groups, for instance, have exactly this role of making things which are abstract more concrete. Again, that's a general idea which is not at the level, the technical level, but it's important to see these ideas also. And then we have linear representations to, and in physics, these are elementary particles and so on. But then we also have vector spaces. So with vector spaces, do we see an action? Asking the audience, which is only Sunil. So scalar multiplication is, of course, we know multiplying vectors by scalars from a field. So now if we look at it as a morphism, then we see the same general pattern of a morphism of an object to the automorphisms or symmetries of another object from a different category. But here, automorphisms of V, just with addition, as an abelian group. these are things which are not disclosed in abstract algebra, for instance, when we talk about algebraic structures. And we are leaving the students just with the bare effects and the, let's say, lower technical level, which has to be introduced, but then a little bit of salt, as I said before, might be useful to give. And then, of course, as Charlotte noticed or said at some point, well, modules, of course, are modules like vector spaces, except instead of having a field, you have a ring. So, since I started in this direction right now, we have to mention at least the idea of module. And then, what are abelian groups? Well, Z modules. And as I would later, I will talk about differential equations and Picard theory, where we have an operator acting on the module. We also have a multiplication, and then it acts through the Leibniz rule as if it's a derivation law. Then we can do calculus. Those are called P modules. So these are more complicated structures, but then you see how we unify somehow these structures. They are all of the same kind. A morphism from an object to the automorphisms of another object from a different category. But that's maybe too much for this talk. And coming back to Felix Klein and abstract geometry, in particular, the above groups of transformations are subgroups of projective transformations. And then I'll just coin something, let's say, quite deep. That's why physics is conformal. We all have heard about Maxwell equations and electromagnetism as being a conformal theory, and which means preserving angles. But then we all know that reality is governed by distance, by metric, because it matters how far you are from the point where you want to go. But on the other hand, it turns out that physics theories at the fundamental level are conformal, which correspond to projective transformations of a certain kind. So now, let's move on to Sophus Lee and differential equations. If there are no other questions at this point or comments. So Klein and Lee were good friends most of the time, I guess, talking mathematics, and as a math team, trying to understand it. Actually, I meant like a team that we should try to understand how it worked and how it helped developing mathematics. Through collaboration and all that. Then another example that came to mind, maybe not quite related, but it's fun to know that Descartes, for instance, was playing cards with Pascal. And then Pascal started developing probability theory. That's again, I think a fun fact to give more more human kind of character to what mathematicians are doing and so on. Then Klein unified geometries, and Sophus Lee tried to unify differential equations, trying to use Galois principle, namely to a differential equation associated with a group of transformations. Now, as a side product of this work, the theory of Lie groups emerged, and that's very important, and then theory of Lie groups and the algebras. And then point to another aspect that usually we think of calculus and derivatives in terms of limits, and we all the time require to have the real numbers and the continuum, and this makes us stuck in the classical era, 1800s of real analysis and all that. But we all know that reality is quantum, everything is discrete and so on. But then how do we get rid of limits and real numbers? How do we do calculus? Well, to do calculus, you need to have a derivative, a derivation law. And this can be done algebraically. That's another important idea. So I did it here. Calculus, we need a derivative and then, of course, solving differential equations, we need amounts to having an integral. This can be achieved without limits and real numbers, and the framework is called differential algebra. I provided a link. And by the way, for example, in VOAs studied by Gale, she mentioned the structure of a Leibniz algebra, which actually is a modification of a Lie algebra, where each right multiplication, say, by the algebra element is a derivation. Now, that corresponds to the concept of connection or derivation law in differential geometry. I won't go further with that. But that also supports this idea that you can have a calculus just by having an algebraic structure together with such an extra structure given by derivation. And then to support that, we don't necessarily have to have real valued functions. I want to mention the so-called Newton's dream. He somehow hoped that, or wishful thinking that if all the functions would be representable as power series, then differentiation and integration would be a breeze, because you differentiate term by term, you integrate term by term. Let's call this Isaac Newton's dream. But power series are an algebraic construct, like infinite polynomials. Then the complications involving convergence come from the real numbers. Continue. Okay, so let's move on to a modern reformulation of Galois theory, which was done by Artin and after some developments. Hi, welcome. After developments by Noether, which is considered to be the father of modern algebra. And for example, in the theory of rings, there is a so-called Noetherian rings area studied by her and named after her. And later we'll talk about her contributions, bridging mathematics and physics. But for right now, with this new modern algebra developed, theory of rings, modules, Artin reformulated Galois theory in terms of fields and field extensions, and then the corresponding symmetries of these fields with the subfield field extensions. Oh, let's see again the same pattern. A field is like a ring or number system with inverses. Usually we look at number fields, number systems, and then extensions like Q inside, say Q of square root of 2, or some other algebraic extension. Then here you have an object inside a larger object. Then think that the larger object is like the environment. Think of geometries, for instance. Then you have inside, for example, Euclidean geometry. Then you have inside a smaller object or a sub-object. Like for instance, a square, and you look at the symmetries of the corresponding, the smaller object in the larger environment. So then, as you can see, the same idea of looking at symmetries leads to the idea of a Galois group of this is K and that's L. Galois group of the extension of fields L over K. And that again is what I call Galois principle. But if you look back at Klein, that's also the definition of an abstract geometry. So again, it's the same overall pattern, which applies not only to this algebraic context, but also to the geometry context. So Emil Artin reformulated Galois theory and Galois correspondence between fields and their Galois groups or symmetries. There is not much time left, so I'll skip a few slides. Then, Sophus Lee tried to took this idea from Galois and Klein geometry and apply it to differential equations. And longer story short, he then came up with so-called Lie groups, and then the study of Lie groups amounts to the study of Lie algebras, which are a local description near the identity element of the nonlinear structure of the group. It's a linearized version of that structure. So Klein and Lee. Say, use this Galois principle. And then, plus modern algebra, we had Artin's version of Galois theory for polynomial equations. But then you might think, what about differential equations? Can we reformulate the Lie theory regarding differential equations and differential Galois groups with the modern language? And indeed, this was done by Picard and Bessieux. In terms of differential fields, well, no surprise there, right? So you have the fields structure, it's algebraic, but then you have a derivation law. And these models what happens when you study differential equations and the corresponding solutions, which are transformations, which can be composed and so on. The theory. So Picard reformulated this in terms of differential fields, and then actually differential Galois groups. And at this stage, I don't want to go too much into details. Just mentioning this general idea that differential equations are abstracted as differential fields and then studied as extensions of differential fields in parallel with the theory of algebraic field extensions. So still, I want to spend a little bit more time. So you have polynomial equations, And then you have differential equations. Then you have field extensions. Obtained by adjoining roots. Well, formal roots. Like q of square root of 2. And then the same idea carries over to differential equations. You have differential field extensions, which means what? You have a field of functions, and then you adjoin some formal solutions to your differential equations. Your differential equation. So no numerical approximations, no. It's an abstract viewpoint, but it's so natural that that I wanted to kind of share it with you. So this is as if we're introducing new functions abstractly through their properties, not constructively in a different way, like in real analysis or numerical methods. So I'm almost out of time, so I'll just mention Noether and her contribution joining mathematics and physics. Again, using this Galois principle that if you want to study a physical system, then look at its symmetries. And then Noether showed that the symmetries of a physical system correspond to conservation laws. But what are conservation laws? They are primitive integral solutions. So this is like taking the Picard theory regarding differential equations and then applying it to physics. But her work and theorems do not do that explicitly. So there's some room for development using some abstract algebra to understand Noether's theorems. But again, see the similarity. Conservation laws are integrals, like energy corresponds to invariance to time translations. So then it's clear that here there is a project where you can start to look in more depth to Noether's theorems from the point of view of abstract algebra and the Picard theory of differential equations. And then beyond Noether's, there are some recent articles where I pursue this idea of periods, but there's not enough time right now to talk about that, which lead to the larger program to show that natural laws are in fact mathematical periods laws. Periods are some integrals, but they're algebraic integrals. So with this, I think I should stop here, and then I'll continue part 2 another time. So
Let's thank Lucien.
thank you for the audience, and thank you for the online audience. Bye.
Thanks for coming.
Thank you.
And